Welcome. This is lecture 8 of module 2 on thin film deposition. In the previous two lectures we discussed about plasma and plasma physics, and in those lectures we mainly concentrated on how to create plasma and how to sustain plasma. Okay, and we also know that plasma consists of electrons, positively charged gas ions, and also neutral species, neutral gas atoms. Okay. Now, in the following 2 or 3 lectures, we will discuss how to use this plasma for a physical vapor deposition process or PVD process called sputtering. Okay. So, first look at what happens when ions which are in plasma interact with the surface. Okay. So, we will start with ion surface interactions. Remember when we were discussing physical vapor deposition techniques, we had discussed there are two techniques or two broad categories. One was evaporation and second was sputtering. Evaporation was by heating the material, and sputtering was mechanically removing the material from the source. Okay. So, in the sputtering process we will use these ions which are in plasma. So, our plasma has electrons plus ions, most of them are positively charged, plus neutral species of gas atoms that we are using to create plasma. Okay. Gas atoms. Okay. We can use many types of gases. We can use noble gases like argon, helium, xenon, etc. to create neutral plasma, or we can use oxygen, nitrogen, and sometimes ammonia, these gases, to create plasma of these gases or ions of these gases, which can be used for reactive sputtering. Okay. Now, for sputtering process we are mainly interested in these positively charged ions. What happens that if you recall our cathode, which is a negative electrode, all positively charged ions will be accelerated towards the cathode. Okay. So, in the electric field which is applied between the two electrodes. Now, these positively charged ions which has certain some kinetic energy, when they collide with the surface of cathode, there are many activities that happen on the surface. Okay. Some of these are that these energetic particles will go deep down into the surface of the cathode. In this lecture and the lecture following this, we will call cathode as our target. Okay. So, our cathode is our target on which we want to bombard these positively charged ions. So, some of these will be just reflected. Okay, they will collide with the surface and will be reflected back. Some of them will displace the surface atoms of the target and get implanted. So, they will go deep down into my cathode or the target. They may also get adsorbed on the target. If they have low energy, they will just come close to the target and just sit there and do nothing. Okay. They can also react with the target. If we are using any ions of a reactive gas like oxygen, nitrogen, etc., then they might react with our target. Okay. And in various processes they might also create lattice defects in our target. They might also move deep down into a target by a process called channeling. Okay. So channeling is the process when you are when these positively charged ions find channel between two lattice planes of the target, and then they feel no resistance due to the atoms, because they are moving in between planes, in between the planes of atoms of the target. So they can just move without much resistance deep into the target, and this is a process called channeling. Okay. Now the process we are interested in is called sputtering, in which through a cascade of collisions these ions will result in sputtering of the atoms or ions from target. Okay. So it is the target uh, material that we want to deposit as thin film. Okay. And these energetic ions will transfer their energy, their kinetic energy, to the atoms or ions of the target material, which will then come out of the surface, and we can use these sputtered atoms to deposit thin films. So we are mainly interested in the sputtered atoms. Okay. Now let us have a look at the energy distribution of the ions in which many of these activities of ion surface interaction takes place. So as you see, on the y axis we have a coefficient called sticking probability alpha, okay, and here we have kinetic energy of ions which are bombarding the surface of my target. We can see if the kinetic energy of these ions is very low in terms of electron volts, then either they will just form a condensation, they will just get physisorbed without any chemical interaction between the target and the ions on the surface of my target. If they have slightly higher energy, they may form a chemical bond with the surface. It may be van der Waals forces as well, and they will get chemisorbed. Okay. So we are not interested in these low energy ions. Okay. If we increase the energy, on the other hand, then these ions will go deep inside the target material and get implanted there and stay there, and that is why the sticking coefficient is very high, because they are going inside the target and just sticking there. On the left side, they are just staying on the surface and sticking there. What we are interested in the energy range where the sticking probability is very low, in this range. Okay, where the sticking probability is low, which means that these ions recoil from the surface. Okay, in the process of recoil, the momentum transfer, they transfer their energy to the atoms of the target, and when they do that, these atoms which are on the target surface will come out with certain kinetic energy, and we can use these for thin film deposition. Okay. So we are interested in the energy range of around few hundred electron volts up to for sputtering process. Okay. So we need to get our ions to these energies. Okay. Remember, we are discussing a parallel plate geometry right now, okay, with the applied voltage, and we have a negative and positive electrode, and our negative electrode is our target. Okay, and our and positively charged ions are accelerated towards this, okay, and result in sputtering of these atoms from the target, and we can keep our substrate at any place where they will reach and form a thin film. Okay, and we have a plasma here in between these two electrodes. Okay. So, how many atoms are being sputtered from the target? It's a quantity that we define as sputtering yield. Okay, and sputtering yield depends on number of sputtered atoms divided by number of impinging ions. Okay. So, for each ion that is bombarded on the surface of the target, how many atoms are being sputtered? Okay. And of course, we would want that for each ion more and more number of atoms from the target are being sputtered, so that we can use them these sputtered atoms for thin film deposition. This table here gives an idea of different sputtering yields for different metals under different plasma gases. So, these are my plasma gas or plasma species, and these are or the sputtering gas, and these are my metals or the target of which we make our cathode, and these are at different energies, and a comparison between argon at higher energy and a 0.5 kilo electron volt. Okay. So, you can see in some cases the sputtering yield is very high, and in some other cases the sputtering yield is very low. So, you can choose your plasma species according to what you want to deposit. Okay. And there is a threshold voltage for sputtering. How much is the energy of the ion should be there, so that you can start sputter, and this threshold voltage depends on how strongly these atoms of the target are bonded together. Okay. So, at what energy, if the ions are approaching, they will be able to sputter, and this is a quantity called threshold voltage. Okay. So, and you can see that sputtering yields for different metals in a same sputtering gas vary very differently in a large scale. Okay. So, we should also keep in mind that sputtering yield for different elements is different. And what are these sputtering yields depend on? That list down some of those properties. Sputtering yield depends on the position of element in periodic table. Okay. Number 1. Number 2, it depends on the crystal structure, and even in the same material, the closed packed directions have high sputtering yield. Okay. You can think of this that if you have a closed packed direction along which my ion is bombarding, so it will interact with more atoms of the target or of that material, and will be able to transfer its energy to more number of atoms. Okay. And then our sputtering yield would be higher. Okay. Also, it depends on the it also affects the energy distribution of sputtered atoms or ions. Okay. The sputtered species from the target can be atoms or ions, or in some cases even molecules. Okay. Now, the energy distribution, because we do not want all these material to just come out of the surface and just sit there, they have to have certain kinetic energy to move towards the surface or the substrate where we want to deposit the film. So, the energy distribution of sputtered atoms lies around 2 to 7 electron volts. Okay. And of course, you can adjust this by adjusting the energy of the ions that you are bombarding on the surface or the target. Okay. It also depends on angular distribution of sputtered atoms. Okay. So, these atoms, when they come out of the target surface, they will have certain angle, they are not just coming out straight. Okay. So, there will be an angular distribution. Okay. For high energy ions bombardment, this distribution will be very narrow. Okay. Or if you recall that the coefficient that we had used when we were describing the directionality of the source. So, n will be high for high energy ions bombarding on the surface, okay, and n is the directionality, and n will be low for low energy ions. Okay. So, the energy of the ions will also define how spread out these atoms and ions coming out of the target will be. Other important parameter is incident angle of ions. Okay. At what angle they are approaching, these energetic ions are approaching the surface, and this is very important because you can see in this graph here that how the yield varies with an angle theta. Okay. And this is a yield for theta, and yield for theta is equal to 0, means if you are coming straight at the surface or the target. Okay. So, if you are coming straight and your sputtering yield is 1, then if you increase the angle up to around 45 to 60 degrees, your sputtering yield increases. Okay. And then it starts to decrease when you are coming at very acute angle. Okay. So, towards the surface. Now, it should be evident then if a ion is coming straight at the target, it will try to push the atoms of the material in deep inside and not will be able to remove these atoms from the surface. And if the ion is approaching at an angle, then it will just transfer its energy and will be able to knock out the atoms from the surface. So, the sputtering yield increases, and then if the angle is very narrow, or from the normal to the surface it is close to 90 degree, then they will just glance off from the surface and will not be able to transfer the energy. Okay. So, incident angle of ions is also very important. Okay. Now, when these energetic ions are being bombarded, remember we had said that closed packed directions have more sputtering yield, and the less closed packed directions have a different sputtering yield, and this will also create different sputtering yields in different directions. Okay. But if in the process, due to damages created by these sputtered atoms, creates an amorphous structure locally, then the directionality or sputtering yield at different places will be same. Okay. So, if you have a polycrystalline material, you would have certain atoms, certain grains which are oriented favorably, some grains will be oriented unfavorably for sputtering. But due to the first wave of ions, it will try to create defects and amorphize the layer, okay, and then the effect of crystal structure vanishes, and then you get uniform sputtering from entire surface of the target. Okay. So, this amorphization of surface happens during ion bombardment. Now, if you have your target at a higher temperature, then you would be able to anneal these defects, and then your target will become again polycrystalline. Okay, so you can decide by if you want to do at room temperature or a higher temperature, or you need an amorphized surface for sputtering or not. Okay, for various depositions or different thin films. Okay, you can also sputter molecules. Okay, and sometimes even organic small molecules have been reported. Now, organic molecules are soft material. It is counterintuitive to think that you will be able to sputter these molecules, but in fact you can under certain conditions you can also sputter these organic molecules from a target. Okay. So, this is about sputtering yield and how the sputtering process from the at the target happens. Now, the most important part, it's sputtering of alloys. Okay. If you recall that when we were doing thermal deposition or thermal evaporation, we had said we cannot have maintained the stoichiometry for thin film deposition because of the difference in vapor pressure. Okay. In thermal evaporation, it was the difference in vapor pressure. Okay. Now, here also we have, if we take an alloy of A and B, so this is my alloy of a composition, let us say Ca and Cb, where Ca is number of A atoms divided by total number of atoms, and C is number of B atoms divided by total number of atoms. Okay. Now, Ca and Cb will also have different sputtering yields for a given energy of ions. Okay. So, energy of ion is fixed because our target is same made of an of alloy called Ab, okay, with certain composition. Okay. Now, sputtering yields are different, Sa and Sb. Okay. So, the sputtered flux will depend on the concentration and the sputtering yield. These are the sputtering yields. Okay. So, the sputtered flux or the ratio of the flux psi phi of A and psi of B will depend on Sa Ca and Sb Cb. Okay. If Ca is higher, then for the same Sa over Sb, there will be more A sputtered. Okay. Or if the concentration of B is higher in the alloy, then for the same sputtering yields, more B will be sputtered. So, in the flux or the material which is coming out and going to be deposited on the surface or substrate, my psi A and psi B ratio is like this. Okay. Now, if Ng atoms or ions are impinging on target, which is alloy Ab, then the total atoms coming out of A and B would be Ng Sa Ca, okay, and also Ng Sb Cb, okay, because Ca is the concentration and the sputtering yield depends on number of ion impinging. Okay. Now, say after certain time t, some time, okay, because let us assume that Sa is much greater than Sb. So, more of A being sputtered. If more of A is being sputtered from the surface of the target, then my target is getting richer in B. Okay. So, my concentration will change. This is the surface concentration. Surface concentration will be Ca dash over Cb dash, which is equal to Ca Now 1 minus Ng Sa over N, okay, and this is divided by Cb 1 minus Ng Sb over N. Okay, so Ca and Cb was my initial composition, but after sputtering for some time t, when some atoms of A and B have sputtered, my surface concentration, the ratio of the surface concentration will be like this. Okay, so now if Sa is higher than Sb, we know that Ca dash over Cb dash would be less than Ca over Cb, and this is from this expression, because Sa is higher, Ca over Cb, then Ca dash over Cb dash would be lower than Ca over Cb. Okay, so my target is now richer in B. Okay, so if we calculate the flux again from this composition, we will see that psi A dash over psi B dash will be equal to Sa Ca dash over Sb Cb dash. Okay, now the sputtering will depend on the new composition. Okay, and where Ca dash over Cb dash is this expression. Okay, now if Sa is higher than Sb, at some point psi B dash will be higher than psi A dash. Okay, here psi A was higher than psi B. Okay, now I have more sputtered flux for B. Okay, now this change between higher flux of A and higher flux of B will eventually reach a steady state, such that in steady state my composition becomes that Ca over Cb dash is equal to Ca Sb over Cb Sa. Sorry, this is my in steady state, and this is surface composition. Okay, a steady state will reach where my surface composition will become this, and then if I calculate the flux from this surface composition, I will get psi A double dash over psi B double dash will be equal to Ca over Cb. Okay, from this surface composition. Now if I have this, then I know, because this is the flux ratio of material in the flux in the vapor phase. So this is the composition deposited as thin film, which was our goal to start with. Remember, our target was this Ca and Cb, and we wanted to deposit the film of the same ratio Ca over Cb, and we have achieved that. Okay, but my surface composition is different. Okay, surface composition, not the target composition. Target composition is still Ca over Cb, but this instantaneous, the dynamics between how much the sputtered rate and the composition will play out such that you will get a steady state deposition of the composition that you want. Okay, so now you can see that we can use sputtering for deposition of alloys without losing the stoichiometry. The only condition is that you should allow time for pre-sputtering. Pre-sputtering means it has two reasons. That first, you can remove anything that is deposited on the surface or adsorbed, any gases, any unwanted species, remove that. You are not depositing on your surface is blocked by a cover. Okay, so your surface is blocked, so that you are not depositing anything unwanted on your substrate, and you are doing sputtering process here. Okay, and so remove unwanted species, and second, achieve steady state surface composition. Okay, and it will take maybe a minute or 5 minutes. of sputtering to reach this. Okay. So, the steady state surface composition, which is this, okay, and you can calculate what would be the steady state surface composition. So, once you reach this steady state surface composition, you can remove the shutter in front of your substrate and allow this flux to be deposited on the surface or the substrate that you want to deposit thin film. Okay. So, in this way, this is a superior technique compared to thermal evaporation. Okay. And this is we will see more benefits or more advantages of a sputtering process over thermal evaporation in the coming lectures, and various ways to do of doing the sputtering process. Okay. Thank you very much.